Hi everyone, and welcome to Module 9 of MA 215, Applied Statistics at Bellevue University. I'm Professor Brame, or Professor B. Last week, we talked about the normal model and how to do confidence intervals on a hypothesis testing using proportions. So this week, we're going to talk about Gosset's t-distribution. Gosset's t-distribution is how we're going to do hypothesis testing and create confidence intervals using means rather than proportions as we did last week. Now, 2 weeks ago, we talked about the central limit theorem and how when we met certain requirements, we were able to then use a normal model with a mean of mu, which was the population mean, and then the standard deviation was the population standard deviation divided by the square root of n. Now, last week when we talked about proportions, we didn't have the population proportion, or p, and so we had to replace it with p hat. So remember, last week we used something called standard error, which ended up being p hat q hat over n. This week, because again we don't have the population standard deviation, now we're going to have to use our sample standard deviation, which we just call s. So again, this week, because we don't have that sigma value, we're now going to use S, which is of course our sample standard deviation. So just like last week, we're going to base everything off of data that we gather. And again, we're going to call this the standard error. Now we have a little bit of a problem, however, because we have extra variation in our standard error because we're using S instead of sigma. And so in fact, this doesn't really fit a normal model like it did last week. So now we have to think about what model can we use. Well, William Gosset worked for the Guinness Brewery in Dublin, Ireland, and he was working basically to find the best yielding varieties of barley for the brewery. And for obvious reasons, because he had to do some serious sample testing, he needed a small sample size, so he didn't want to just be getting wasted at work every day. So he was working with Carl Pearson, which is another researcher, and together they came up with this new model. And basically what the new model did is it accounted for that extra variation. So they normally would name this like Gosset's T, but Guinness had prohibited its employees from publishing any papers because some other guy who used to work at the Guinness Brewery basically published a paper containing their trade secrets. So unfortunately, Gosset was reduced to something called student. So we call this, instead of Gosset's T, we call it the student's T. So last week we used the normal model. This week we're using the student's T model. Now a normal model is just one curve, but the student's T is actually a whole family of related curves, because for every degree of freedom we have, that curve is going to change just ever so slightly. So degrees of freedom are going to help us to know exactly what that curve is going to look like. And then when we're finding our test statistic, which last week was of course our Z, this week we're going to find a T, and typically we'll put that degree of freedom as a subscript. So this gives us a really good idea of the difference between the normal model and the student's T model. So the normal model is this dotted line that we're very familiar with. The student's T model, as you can see, very similar, but let's look at the differences. Our mode is not quite as high because these tails are fatter. So the student's T has fatter tails than a normal model, which means when I'm making my confidence intervals, they're going to be a bit wider and the p-value is just a bit larger because there's extra data down here. So there's extra area down there. We use a T model with n minus 1 degrees of freedom, and of course n is the number of observations. And essentially what that's going to do is create the precise T model that we need, and then we can do our calculations as we did last week. It should be noted that as the degrees of freedom increases, the value or the T model is going to be more and more normal. So this is with 2 degrees of freedom. With 3, this would sort of move up, and these would then skinny out a little bit. With 5, even more so. And then if you have an infinite degree of freedom, then it's going to look exactly the same as the normal model.